I'm Susan Faraday. I'm the director of the Marine Affairs Institute here at Roger Williams University School of Law. I also direct the Rhode Island Sea Grant Legal Program. And we're just going to get right into the program. We have a dense and beefy and challenging and interesting program for you the next couple of days. And it couldn't have been more timely. So we have a lot to do, we have a lot to talk about, and I'm going to turn it over right now to President Donald Farish, President of Roger Williams University, to welcome us.
Thank you, and thank you, Susan. I want to start by commending Susan and her colleagues in the Marine Affairs Institute for putting this program together. I read through the biographies that she gave me, and there's a very impressive group of people in this room, but you already know that because you've read the biographies as well, or you own one of them, as the case may be. So it's great to have you here at Roger Williams University, and I think that if I want to make a point here, it would be more or less as follows. Most of the serious social problems facing our world today are inherently interdisciplinary. They just cannot be resolved by expertise from one area. They require looking at a problem from multiple perspectives, and that's something that we really try and emphasize with our undergraduates here at this university. We have a bewildering array of professional programs as well as a full complement of arts and sciences, and so we've been stressing to our students the need to be able to have strengths in more than one area. So if they're majoring in the liberal arts, we want them to take a minor in the professional programs and vice versa. And this is working out in some rather interesting ways. The great fear that parents have these days is that their children will graduate in debt with no job. And when I mention that to a parent, they sort of sit up straight like I just hit them with a hot poker, because it is their great fear. Their children will come home, live in the basement, and they'll never emerge again. So all of that investment in their future was for nothing. And so we really want to try and overcome that here. And this kind of symposium is an exemplar of that type of thinking. And it's interesting how this works, because I had another example of this last night at dinner. We have on campus right now a Woodrow Wilson Fellow in architecture, just for a few days. He's from California, and he was asking at dinner, we had this large array of people at dinner last night who were doing housing projects around the state. I can't keep them straight. They have different names and different responsibilities. They know how to distinguish themselves. For me, it's kind of a blur and a bit of an overlap of responsibilities. And the fellow from California, big state of course, said, well, are there times when you get together regularly and kind of compare notes? And the response was, oh no, you know, Rhode Island is a small state. We all know each other. And I said, I want gently to disagree with that assessment, because I think the problem is we assume, because we know each other, we have nothing to learn from each other. And I think it's by putting people in the room together, even people who know each other, that the opportunities emerge for collaboration, cooperation, perspectives from a different angle, all the things that really develop from an interdisciplinary perspective that allow us in a far more comprehensive and effective way to look afresh at the problems that our society faces and to conjure up new solutions and new ways of analyzing that problem. So I congratulate you for taking the time today. We've arranged for a cool couple of days here. That's to keep you inside. Because otherwise, on a nice day, you'd be wandering the campus looking at the water because, you know, marine stuff. So, but this way you kind of have to be here. So thank you for coming. Thank you again, Susan, for putting this together, and have a great symposium.
Thank you, President Farish. And it's now my pleasure to introduce Dean David Logan, my boss, and a great supporter of the Marine Affairs Institute here at Roger Williams.
Thank you, Susan. Let me add my welcome to that of President Farish. And by the way, he knows of what he speaks in terms of cross-disciplinarity. He has a JD degree and a PhD in biology, so he really does appreciate the kind of synergies that come when you put people in the same room, talk about the same problem from different perspectives. I also want to congratulate Susan. This is really a home run for you and Julia and your staff. It's a really terrific gathering. Needless to say, highly topical and timely. And I want to give you a little bit of background very quickly. I'm not big on speeches, but I want to give you a little bit of context about the Marine Affairs Institute. It was founded in 1996 in our third year of existence as a law school. Yes, we've only been around 17 years. We've done a lot of important things in that time, but none more important than the programs we sponsor through the Marine Affairs Institute. It was about a year and a half ago we did a major program on oil pollution and the deep water blowout in the Gulf. We've done very innovative programs on marine renewable energy, on shipping questions, and the Marine Affairs Institute is just what Dr. Farrar suggested. It's an opportunity to bring together professionals to debate and hopefully help solve really major problems that affect certainly Rhode Island and the Eastern Seaboard, but really the country and the world. And one of the nice things we do here, again, building on Dr. Farrish's observation, is with the assistance of Rhode Island Sea Grant, we are able to have law students serve as research assistants or actually do research projects for nonprofits around New England and actually in some cases around the country, so they can hone their skills as lawyers and policymakers while they're still in law school. And the result of this has been terrific because I guess virtually every year we have at least one, if not two, Knaus Fellows, and it's really a testament to the fact that they're getting good book learning here as well as good practical skills. We have a very deep curriculum in marine affairs, marine law, environmental law. So the students we draw here, many of our very best students come because we're one of the very few programs in the country that focus on marine law with the kind of depth and breadth we do. I want to thank, of course, our sponsors for the event, the Conservation Law Foundation, the Hanson Curran firm here in Providence, the National Marine Sanctuary Foundation, and the Coastal States Organization. And before we go into the formal program, I want to spend just a quick minute. Those of you that are from Rhode Island or those of you that are familiar with marine affairs may know that we all lost a very dear friend this last weekend. Bill Coffey passed away. Bill was a member of our adjunct faculty, but also, importantly, in the period of time we were doing the national search that yielded the wonderful Susan Faraday, he actually directed the Marine Affairs Institute, and there was not a happier, kinder, more student-centered person in the universe, and we're deeply saddened to have lost a very important member of our family over this weekend. And so those of us, and I know Barry, a lot of folks here in the room came in contact with Bill, and I know your thoughts join ours to his family for this really sad loss. Now to the program. Susan Faraday's been with us now for 5 years and has really done a terrific job of integrating the Marine Affairs Institute into the curricular lives of our students and also into the public policy debates throughout the country. She will be telling you more about the symposium and giving thanks to various people here in the building like Chelsea Horn and her staff. These things don't happen just by directors going like this. There's a lot of people that have to make it go. So thank you very much. I'll be in and out in the program. I got a bunch of meetings today, but I'm fascinated by the topic. And now I give you my wonderful director, Susan Faraday.
Thank you so much, President Farish and Dean Logan. It's always a risk to come after Dean Logan. You have to readjust the microphone. So I'm going to tell you a little bit about our event, go over some housekeeping, and just I'm your navigator for the next couple of days. I want to talk a little bit about what this event is and what it isn't, and why we chose this topic. I wish I could take credit for being remarkably perceptive a year ago when we came up with this topic, that there would be this devastating storm that all of a sudden put climate change literally in the mouths of politicians and the media in a way that it hasn't been before. I can't really take credit for that, but it makes what we're going to be discussing the next couple of days even more timely and relevant. Life on our coasts is changing. Recent events have illustrated how vulnerable our lives, our communities, our infrastructure are along our coasts. And what we're going to be doing today segues very nicely to the introduction by my leaders here at Roger Williams. We're going to be exploring two very complex systems, our system of law and our ocean ecosystems. Law governs the many ways that we conduct our lives on the coast. Those of us who are lawyers in the room know that law is the rule book. It makes us play nice with each other and helps us resolve conflicts and plan our lives in an orderly way. The way this works on the coast is it really guides where we build our homes and our businesses, how they're insured, how our infrastructure is developed and sited, things like roads, sewer treatment plants, and how local fisheries are harvested. So the law really gives a framework, the playbook, if you will, for how we conduct our lives along the coast. This is all based on assumptions about the marine ecosystem and how our climate functions. Those assumptions are being turned on their head. And we very deliberately have integrated a lot of scientific information into this symposium so we could really get the most up-to-date information on the various ways that we're seeing signals throughout the marine ecosystem of how these assumptions are changing. So if you think about how a decision is made about where to site a road or a sewer treatment plant on the coast, and you have a whole new set of different floodplain maps or information about increasing sea level, that may inform your thinking about how to proceed in the future. We've really gathered an amazing group of folks here. I'm going to spend less time today talking about each of their backgrounds in depth when I introduce them, but I really encourage you to browse through the program, which you have in your hands if you're here in person, and you can access online if you're participating via webinar. We've arranged scientists, social scientists, natural scientists, insurance people, a wide array of lawyers, both in the private practice and public practice, nonprofit organizations. We really want to take a complex look at a very complex topic to help inform how we're going to participate in these decisions going forward. We are quite deliberately focusing just on the impacts of climate change on the oceans. This is not all things climate change, and it's not all things ocean either. If you take a look at the program and you take a look at the panels, we could spend 2 days on almost any of them. And instead, apologies to all the panelists, I know you'd like to talk for more than 15 minutes, but we don't have 2 days for your panel. We only have the hour and a half. But we've done that deliberately to give you really a lot of snapshots, so we get a sense of what's going on in the Arctic, what's going on near shore, what's going on with the animals that live in the ocean, what's going on with economic impacts. We really want to take a broad look at all these snapshots. So my lawyers love disclaimers. So my first disclaimer of the day is this is not all things climate change, and it's not all things related to oceans and climate change. But I hope it's a pretty good whack to get us a sense of where we are. We're also taking what one of my very good friends and colleagues says is a global approach, going from global up at the Arctic ice cap with colleagues from Norway here to present, to colleagues coming from San Francisco, from Texas, from Louisiana, to right here in Rhode Island. We have a lot of folks here in Rhode Island who have had a very eventful couple of weeks in the aftermath of Superstorm Sandy. So that's the range of what we're going to be talking about today and tomorrow as well. I need to do all my thank yous now. As Dean Logan said, these events don't just happen in isolation, and although I stand here and do a lot of the talking, there's an immense array of support people that help make this happen. So thank you to my good colleagues at the Marine Affairs Institute, Julia Wyman and Charlotte Ferris out at the registration table. Give Charlotte a big hug. She's really responsible for all the things that make this event a really nice one for you as participants. My advisory board, many members here who are also on the planning committee and will be moderators, and I ask them over and over again to do things, and they always say yes. So thank you, advisory board members. And we have tremendous support from the university. So we have instructional design and media services helping us out with webinar and recording. We have facilities management, we have catering, we have media support. So thank you to all those folks for making this possible. And before I get into the housekeeping and we launch into our program, I just want to also share a couple of thoughts about Professor Bill Coffey. And it's appropriate to have this event and talk about Bill a little bit, because no matter what I asked him, Bill would always say, "I'm happy to do it, Susan." Bill, you want to be on an advisory board? Happy to do it. You want to design a new course for us? Happy to do it. Want to talk to some prospective students? Happy to do it. So I'm happy to be here and carry on Bill's legacy of service to the marine profession very broadly. And those of you who knew him either as a colleague or as a student, think a good thought for Bill today. Okay, housekeeping. So we have attendees in the room, we have attendees online as well, so we're going to be paying close attention to audio. And webinar participants and live participants, we're going to hold questions till we get to the end of each session. So if you got a burning one, jot it down. We will be shepherding the questions from the webinar attendees, as well as those of you in the room, to the moderators to orchestrate all this, and hopefully it works well. We will be posting both the presentations and recordings of all this on the website afterwards, so you don't need to exhaust your wrist trying to take notes. Bathrooms are located just out across the hall. The break stuff is all where you saw it today. We try to keep everybody fairly well caffeinated and nourished during these events. We have an evaluation form in the folder, and webinar participants, you have an evaluation form. Please take a look at that. Keep track of what you like, what you don't, as we go through our program. We really value your feedback. I'd like to ask you to respect the speakers that we've invited here. I know we all multitask an awful lot, but please mute whatever device you have. I'm not advanced enough to have a smartphone. I call mine a dumb phone. But please mute that and try to keep your multitasking to a minimum because we really do have a great array of speakers here to present their information to you. So I'm delighted to welcome Dr. Bill Curry back to New England. Dr. Curry is president and director of the Bermuda Institute of Ocean Sciences. Just started in September, yes? And prior to that, he was just down the road at Woods Hole Oceanographic Institute, where he directed their Ocean and Climate Change Institute. Again, I'm not going to go through his bio, but take a look at it. It's pretty cool. Dr. Curry studies the history of climate and ocean circulation, in particular how large changes in ocean circulation and chemistry have affected the carbon cycle and ice age climate. He's participated in 13 oceanographic expeditions, advises all kinds of people, and really knows what he's talking about. It's always a little dicey when you try to invite scientists to talk to lawyers and lawyers to talk to scientists. We oftentimes have some different languages, and when I was looking for a speaker that could talk to a smart but lay audience of non-scientists and give us a big picture view of what's going on with oceans and climate change, Bill was recommended highly and has been a delight to work with, and I'm sure we're all going to enjoy your presentation. Dr. Bill Curry.
Having me. You may need to turn the lights down a little bit for part of this talk, if that's okay. So I was asked to give an overview of the climate changes that are ongoing and likely to happen in the future with particular reference to the oceans. And so what I'm going to try to do here is to start to talk off with just a little bit of background about the greenhouse effect and why certain things in the climate system are inevitable as long as CO2 keeps rising in the atmosphere. Show how the changes in the energy balance of the Earth are affecting different components, including the atmosphere, the oceans, and the ice that's on the surface of the Earth. And then finish off with a little bit about what the CO2 changes in the atmosphere mean for the chemistry of the oceans and the likely future changes in things that are called ocean acidification. The fact that the ocean chemistry is going to change because the ocean acts as one of the receivers of the CO2 that's in the atmosphere, ultimately will be absorbed by the oceans in a long period of time, but is happening as we speak. So the first part, there's no doubt that CO2 is increasing and increasing rapidly since the Industrial Revolution. If you look at this plot, 10,000 years ago, and for the last 10,000 years, the CO2 concentration of the atmosphere was more or less constant at about 275 parts per million. What that means is that the carbon systems that control how much CO2 is in the atmosphere have been stable for that period of time. It's known as the Holocene in geological reference. It's the warm interglacial when all of civilization as we know it evolved. At the start of the Industrial Revolution, CO2 rapidly increased, and now it's actually up around 390 right now. This is a figure from the year 2007. You may ask how we know this. Well, these samples right here are taken from trapped gas bubbles in ice cores, which you can actually count the number of years back and figure out how old the sample was. So they're real measurements of the atmosphere. This high value up in here, up around 390, is actually higher than it's been directly measured for the last 800,000 years. We have 800,000 years of ice core measurements of previous atmosphere to know that this is well out of whack. And in fact, you probably have to go back about several tens of millions of years to get this high a value. Now, this alone is not that big of a deal. You know, the amount of CO2 in the atmosphere now is enough to cause a perturbation, but it isn't necessarily a large perturbation. But if you follow the likely scenarios of future CO2 in the atmosphere, given the types of economies that we have and their dependence on fossil fuels, it's, oh, sorry, wrong one. It's not difficult to see that by the year 2100, atmospheric CO2 could be double or triple of what it was in the pre-industrial value. And it's really these types of changes in the future that are the most alarming in terms of what climate changes might bring. Okay? Now, the greenhouse effect, just so you're aware of it. During that period of stability for the last 10,000 years prior to the Industrial Revolution, the Earth's energy system was in balance. What that means is that the amount of energy that was coming in from the sun was equal to the amount of energy that the Earth was radiating back into space. And that's because the planetary temperature was more or less constant. But it's a complicated system. Because there's greenhouse gases in the atmosphere, some of the radiation that would otherwise go out to space is back radiated down, and some of the incoming solar insolation is directly reflected back. These things, these internal processes, are the things that are changing. This is changing because ice tends to be reflective, and the sun's energy hits ice and a lot of it goes right back into space, and it tends to keep the planet cool. This is changing because we're adding greenhouse gases and trapping more heat. So right now, there's an imbalance between the amount of energy that we're receiving and the amount that we're radiating back, and that's why the planet's warming. And it's inevitable. It has to happen, okay? The rate at which it happens and the magnitude is very difficult for climatologists to predict, but the trend has to be there. Now, that extra energy that's being trapped on the surface is going into several locations. Oh, did it again. First of all, the atmosphere. Now, I'll show you in a minute. This is probably what you think of when people talk about global warming, the changes in the atmosphere, the sensible heat that humans feel when they're going about their everyday business. But a lot of it is also going directly into the oceans, and a lot of it is going into the ice sheets. And I'm going to hit each of those components one at a time. So, since about 1880, there's reliable, nearly global records of temperature on the surface, the land and ocean surfaces, mostly land. And what you see is that there's more or less congruence between rising surface temperatures and then the solid line, which is the amount of CO2 in the atmosphere. And it's fairly straightforward to use data like this to come up with estimates of the sensitivity of the planet to rising CO2, the surface temperatures. They vary a little bit, but basically what happens is that the numbers tend to fall out somewhere between, say, 2 degrees centigrade and 4 degrees centigrade. Increase in planetary temperature for every doubling of CO2. We haven't doubled CO2 yet. We've added about, 100 parts per million out of an initial value of 275. But we're on a trajectory to double. So that's why when scientists talk about what you might expect in the year 2100, they come up with an estimate that may be a few degrees warmer than present. It's based on those types of relationships. Now, what you need to know is that, and this is I actually uploaded the latest data, and so over that period of time, there's about a degree centigrade change from 1880 till this past year. But the changes in temperature have not been uniform on the planet. This shows what the warming has been since 1880. I think this goes up to, I'm not sure what the number is, August 2011, what it says. But you'll notice that the high latitudes have warmed more than the lower latitudes, and the land surfaces have warmed more than the oceans. So The larger effects in the atmospheric warming are over land and at higher latitudes. And in fact, the Arctic is warming at about 2 or 3 times the rate of the planet as a whole. I'm going to stop with the atmosphere with that one now and talk about what this is mostly about, the oceans. And we have far less information about how the oceans have changed through time. Atmospheric temperature records are fairly well distributed in space and go back at least to the 1800s or maybe even earlier, in large part because of British colonialism and their penchant for having great meteorological stations and allowing to have long time series of those sorts of measurements. They were really into meteorology, and they were all over the globe at, in the 1800s. And so we have reasonable records for a century or more of atmospheric temperature. The oceans are different. We weren't putting thermometers into the oceans a lot in the 1800s. Some of the earliest measurements of temperature, although Ben Franklin made some measurements of the Gulf Stream and things like that in the 1700s, the first real oceanographic expeditions really date to about the late 1800s. And people did not really become interested in ocean temperature or salinity until submarines were invented, okay? And it was really the Cold War between the Soviet Union and the US that allowed for a remarkable increase in the amount of measurements of temperature and salinity. And that's not because they cared about climate at all. It was entirely because they cared about sound velocity and being able to track each other underwater. But what that means is that our understanding of what the oceans have been doing is only robust back to about the beginnings of the Cold War, which means that our records and syntheses started about 1950. But since 1950, I'm sorry, I did it again, every ocean basin has seen an increase in the amount of heat that it has gained. That portion of the trapped energy that's kept because of the greenhouse effect that's increasing has been going into the oceans more or less continuously since about 1950. Now, the oceans are water, of course, and not air, which means that it takes more energy to change their temperature. So if you have a cubic meter of the atmosphere here and a cubic meter of the oceans here, it takes a lot more energy to change the temperature of the ocean water by a degree than it takes to change the atmosphere. So although the oceans have been storing a major amount of heat, they haven't risen in temperature a lot, which gets back to that surface map I showed you, and that most of the warming is over land and not over the oceans. But it turns out that when you calculate, measure, and synthesize the amount of energy that the oceans have gained, 80% of the change in the energy budget due to rising CO2, the CO2 that we have put in there as humans, has gone into the oceans. So here's a set of bar graphs that show the amount of heat that's been gained by the oceans in 1961 to 2003, or this decade from 1993 to 2003, versus the total on the planet. And you'll see that that and that are very similar in size. Now, the amount of heat gained by the atmosphere in order to cause the global warming effect that you feel and read about is this small little bar right here. The amount of heat that's gone into Antarctic ice is here, glaciers on land is here, Greenland is here. So the ice sheets have had very little heat taken up with them. To look at this in a time series, starting in about 1950, the gain in heat on the land and the atmosphere is right there, and the gain in heat in the oceans is right there. Now what that means is that the ocean is your friend in the climate system. It's keeping the planet from getting warm really, really quickly. But it does have consequences. That heat is affecting the volume of the oceans and increasing sea level. It is part of the imbalance that needs to be made up in order for the planet to come back to an energy balance equilibrium, which means that the surface ultimately will have to warm even more, but it's a delayed process. So in order to reach that 2 to 4 degrees C of doubling. It's going to take longer because the oceans have absorbed a lot of this heat and moved it out of the system for warming. Now, how do we know this, and what should you look for in the future? In recent decade, a project called the Argo Float Program has gone out. And these are basically satellites that are put into the oceans, and they're autonomous vehicles that do what we ask them to do. And basically, they are cylindrical. They're about the size of an adult male, can be lifted by 2 people and thrown over the side of a small vessel. And they have a bladder system inside them that allows them to change their buoyancy. And so they sink through the water column and they measure it, what's going on. They measure temperature and salinity. They sink to about 1,000 meters, more or less. And they stay down at that level for about 10 days. And then they're pre-programmed to change their buoyancy, and they come back to the surface and they make the same sort of measurements. And then when they reach the surface, they make a phone call through the commercially defunct Iridium phone system, a satellite phone system that you may have heard about a decade or 2 ago, that has been maintained for scientific purposes that allows us to get data on a regular basis about what's going on in the oceans. I got this, I had to put this talk together before coming here because they wanted it ahead of time. So on November 6th, I went to the Argo Float location. And on that day, there were 3,573 of these out in the ocean making constant measurements every week or 10 days or so. So we're now getting, and we'll continue to get, really reliable information about how the oceans are changing. If you wanted to, we could upload yesterday's map of these things. So the real-time information is really remarkable for anybody who is interested in learning about how to do that. Now, what's the impact of that? I mentioned that the rising heat content of the oceans is causing an expansion. And through measurements made by satellites using altimetry methods, lasers basically pointing down to figure out how high the ocean is, started in about 1992, and with continuous measurements since then through a number of different satellite systems, it's clear that the ocean sea level is rising at the rate of about 3 millimeters per year, okay? 3 millimeters per year. Now, a decade would be 3 centimeters, and 2.54 centimeters is an inch. So 3 centimeters is just a little bit more than an inch a decade, which is one of the reasons why a conservative estimate of sea level by the year 2100 would be about 10 decades worth of an inch or 10 inches higher. The conservative measurements are more like 18 inches or something like that. But even just with the current trajectory and measurements that we know about, sea level would be about 1 foot or 1/3 of a meter higher than it is today. It's a long-term trend. This figure shows, this end of it right here, that little red line, is that sea level record from the satellite era. And this record here dates back to the late 1880s from globally distributed tide gauges. And what you can see is that there's been this continuous rise in sea level. What you don't see here is necessarily much of an acceleration in recent years. People believe that it is accelerating, but it's so small in the acceleration that we can't really measure it well, accurately. I just got the yellow light. Is that halfway? Good. We're in good shape. But there are reasons why we believe that acceleration is going to happen, and that has to do with the melting of the ice sheets, because that's another component that's related to the sea level problem. So let's go to the ice. Sea ice in the Arctic is really important for the climate system. Now, sea ice in the Arctic is a seasonal thing. Every wintertime the Arctic is dark and sea ice grows back. But in the summertime, it usually reaches a minimum because of melting sometime in the 2nd or 3rd week of September. Now in 1984, this is what the minimum sea ice looked like. And then this past summer, this is what it looked like. I like to do this a lot. Very, very different, okay? This past year was an extreme minimum, a record low in the amount of sea ice in the Arctic. Now that's important for climate purposes because remember I said to you early on that ice reflects energy back into space. It's called the ice albedo feedback. Sunlight comes in, a lot of it bounces off the ice. When there's little ice in the Arctic, more of the energy of the sun stays in the water and warms it. And it's one of the reasons why the polar regions tend to warm faster than the planet as a whole, because they're losing ice and less of the energy is being reflected out. Now, very quickly, just to show you the time series of these changes, since the satellite era of measurements, beginning around the late 70s, you can see that there's begun to be an acceleration in the loss sometime around the mid-1990s, and that in recent years you've had some really record low summer sea ices. And these are the times when you read about commercial shipping starting to go through there. You're getting to have times when there's little enough ice that exploration for mineral and fossil fuel resources is about to start. These are all issues related to the types of things that you're probably going to be discussing here. Just to close the loop on this, this was the summer sea ice minimum this past summer. This was the record low in the past, and this was the average record low over that 30 or 40-year period of the satellite era. So these are getting to be extreme, and the volume of ice is actually also going down, and the last 3 or 4 sea ice minimum were also minimum in volume of ice. So you're losing the ice up there. And some of the best estimates are that in about 30 years maybe, on a trajectory, if you just take lines, regression lines of the current rate of sea ice loss, you might have what I would call a functionally no sea ice summer. Doesn't mean that it would be completely gone, but it would be so open that it would be remarkably easy to work in. Well, not remarkably easy because there are no ports and things like that. But it's the type of thing where you wouldn't have to worry about ice much in the summertime. If there's acceleration of the warming, that could come sooner. But a conservative estimate is, several decades from now, you might have really open water in the summertime. The thing that caught scientists by surprise is that the rate of change that's being observed was much faster than what their models were predicting in the mid-2000s. This is a paper in 2007. And we still haven't figured out how to make an accurate projection of what things are going to be like there in a century. So bear in mind that there's a lot of guesswork about this. Although the trajectory is clearly down, the magnitudes and the timing are not that well constrained. Now, how do we know these things? Well, there are now new observing systems in the Arctic, full-time. And one of the ones I want to talk to you about is called this ice-tethered profiling system. It's a unit that hangs beneath the existing ice, and it has a measuring system on it that goes up and down a wire beneath it, making critical measurements of things like the temperature and the salinity there, as well as the sea ice thickness. And sea ice is dynamic, it flows. It's created generally here, north of Alaska and Canada, in what's called the Beaufort Gyre. See this circular pattern here? If you put one of these ice-tethered profilers through the ice and let it just sit there, it won't sit there because the winds are pushing the ice around, and in about a year's time, it might move the distance of the length of that line to that spot. And the other thing that's really important about the Arctic is that the Arctic is creating ice and then also ejecting ice through the Fram Strait here into the North Atlantic. And you can see that that shows up there. These are model simulations. But right now, if you were to go to a certain website, you could find that each one of these triangles is an existing ice-tethered profiler that's monitoring what's going on in the Arctic right now, the movement, the thickness, the changes that are going on. These are the ones occurring in the Beaufort Gyre. These are real data, and these are the ones that are just getting ready to be ejected south here into the North Atlantic. So it's a dynamic process, very complicated to study, but we're getting to the point now where we have enough information to start really making sound observations and hopefully soon reliable forecasting. Now, the last thing about the ice that I want to talk about is Greenland. This is an old figure from 2004, but it illustrates an interesting thing about Greenland. So Greenland has a high elevation, several thousand meters above sea level at its summit. And it has ice all the way down to the coasts. And every summer, basically, Greenland melts below a certain elevation, but it doesn't melt generally above a certain elevation. And that is the basic dynamic. So where it's cold, Greenland is still probably snowing and gaining frozen water and ice, but losing it at low elevations. And there's a dynamic to this where ice is being formed at high elevations, but it flows toward lower elevations and it starts to melt, and it also reaches the oceans. It's a very dynamic thing. Measurements of Greenland using a number of different land-based technologies seem to show an acceleration in melting of Greenland beginning in the late 1990s. And according to this information, I'm going to use this term, 340 gigatons of water per year is being melted from Greenland, net, which is equal to about 1 millimeter per year of sea level rise, or about 1/3 of that satellite measurement of 3 millimeters per year is coming from the melting of Greenland. Now, this is being confirmed by the greatest physics geeky thing I've ever seen. I'm a wannabe physicist, and I'm not really a physicist. But basic physics, gravity, right, can be used to determine the masses of things on planets. And some really clever person figured out that, hey, if we just orbited 2 satellites in tandem that were constantly making measurements of their altitude and their position relative to each other, we would be able to calculate the gravitational field of the Earth beneath them. I think it's just the coolest thing ever. All right? So imagine 2 very large satellites that have lasers pointing at each other so they know how far apart they are, and they have lasers pointing down so they know how high above the surface they are. Now, the first satellite comes toward Greenland. Well, Greenland is extra mass on the surface of the Earth, and so that satellite tends to be accelerated towards Greenland sooner than the trailing satellite. So the distance between them goes apart. And then when this satellite goes past Greenland, but this one is starting to accelerate, they converge again, right? And so by knowing this, and also by knowing how high they are, they can calculate the mass of ice on Greenland. And that is really cool. Even to a scientist, that's really cool, okay? So these satellites were launched about early 2000s. So they've been up for about a decade. So we're just starting to get the measurements. But what you can see is that since 2003, there's been a steady decline in the total mass of Greenland. That's close to what is measured in the previous slide. You can also see that it changes seasonally. So every winter it gains mass, and every summer it loses. Every winter it gains, every summer it loses. Winter, summer, winter, summer. So it's dynamic. It's hard to measure when you're on the ground, but these satellites are giving us really firsthand information and confirming the fact that on net, Greenland is melting. These are also the first satellites capable of giving us a large-scale picture of Antarctic ice, and it is starting to show signs of melting in these data. And this was much harder to do because Antarctica is a much larger and more difficult place for scientists on the ground to figure out what's going on. Now, why might things be melting more quickly? Well, the ocean has a role in this. Remember I said that ice flows down and meets the sea, actually. It meets the sea in fjords. And that sea actually has water flowing up towards Greenland, and there's exchange of warmer waters and colder waters in these locations, and these are all the fjords along here. And all of the fjords have started to show more rapid melting. And one of the things that we're really interested in and studying right now, we haven't solved this problem, is the fact that basically when you go into most of the fjords, what you find is that the water beneath the surface is actually above freezing. That wasn't really a known fact 5 years ago. Now, we haven't been studying it long enough to know whether it's changing, but the type of work that's going on now is that people are flying up to these fjords and drilling holes and making measurements, and they're finding that nearly every fjord that they look at, the water beneath a certain level, this is 200 meters, 600 feet or so, is above the freezing point of fresh water right there. So all of this warm water is actually in contact with the base of these ice sheets in the fjords. And as the oceans are warming, That means more heat is going to be going in there, potentially accelerating the rate of melting of these land-based ice sheets. And that's one of the reasons why most of the climate projections are minimum estimates for sea level and for melting. We don't really know how much more melting is going to happen, but we expect that more melting will occur. Now, I'm going to finish with one last thing, and this is what we think of as the other CO2 problem. Basically, the system as it is right now includes burning of fossil fuels, which produce a certain amount of CO2 into the atmosphere, and deforestation in some parts of the planet, which is also adding CO2 to the atmosphere. And about half of that is going into the atmosphere and staying there. Another 29% is being absorbed by regrowth of forests elsewhere, as well as about a quarter of it ending up in the oceans. The amount that ends up in the oceans is causing chemical changes that are going to have impacts on ecosystems and economies, perhaps. So CO2 in the atmosphere is actually absorbed into the surface waters, it's dissolved, and it reacts with water to produce what's called carbonic acid. It's a very, very weak acid. It's all part of the carbonate system. Basically, it ends up that calcium carbonate calcification is one product of this entire system, and ultimately the fossil fuel CO2 will end up as carbonate sediments on the sea floor, but that's on geological timescales, not on human timescales. It's the change in this value on the short term that's really critical. So this is another set of measurements that oceanographers are making, and it's even shorter timescale measurements than the others that I talked about, but the CO2 measurements started at Mauna Loa in the 1957, show what the atmosphere has been doing. In the late 1980s, oceanographers started making systematic measurements of this CO2 in a number of places, one in Bermuda, one in Hawaii, and you can see that the amount of CO2 has gone up continuously in that time. But the important thing is this right here, this trend right here is the pH, or the acidity of the water. The lower values of pH means more acid water. So there's a net change in the surface. The ocean is absorbing CO2, and it's changing the pH, and it is likely to have impacts on things that humans care about, particularly in the nearshore environments. First of all, corals, but open ocean organisms that provide a lot of the foundational biological productivity in the marine ecosystem. Commercially interesting and important shellfish are also likely to be affected. Eventually, deeper water corals and other things, because the penetration of the CO2 will head into the deep ocean. So, I go back to this figure. As this number in the future, CO2, goes up, acidification effects will get larger. We don't know what the ecological impacts will be. Perhaps other talks later will talk about those things in a better way than I can, but it's something to remember that it will have economic and local, perhaps legal impacts. So that's my last slide. I think that there are several things about the oceans that are likely to change. You know, some of our knowledge is very strong. Some of it is well beyond conjecture, but not firm yet in terms of our ability to make firm predictions, but the trends are very clear, and so much of what happens in the future is unpredictable to us because I have no idea what future fossil fuel burning will be like. You know, that's one of the big unknowns, is what the trajectory will be of emissions. So thank you very much.
Stand by and
Was it good timing?
Thank you so much, Bill. I couldn't have asked for a better overview, and you're exactly right. We're going to get in much more depth on all of the scientific information that you hit on today. We're going to talk about what's happening in the Arctic. We're going to talk about the effects of ocean acidification on things we care about. Sea level rise is implicated in another one of our panels, so that was a really great overview. So how we're going to proceed now, we have about 15 minutes for questions before we take our coffee break. And so we're going to be doing this again. Webinar attendees, if you have a question, get it in now so we can jot it down and kind of keep it in mind here as we're seeing who in the room has questions as well. We're going to do questions. We're going to have somebody over on that side with a mic to get up to you, and I'll be over here with the mic, and you can pass it down to yourself as you go along the row there. Please identify yourself just briefly with your affiliation and your name so we have a sense of where the question is coming from. So let's open it up to questions live here, and I'm going to check in on the webinar folks.
My name is Caroline Carr.
Wait.
My name is Caroline Karp. I'm from Brown University, and I understood in the recent past we actually didn't have a perfect mass balance on the amount of CO2 going into the atmosphere and whether it was being stored in the atmosphere or the ocean. And as I recall, we were missing about 15% of the CO2 in that mass balance. We just didn't know where it was. Has that been solved?
On what time scale are you saying that we were missing it? Because that's important.
So it was something like 1.5 gigatons of carbon, and I thought that was on an annual basis. We weren't sure whether that was partitioning between the atmosphere, the ocean, or land.
Currently.
Currently.
I think I would agree that the numbers that I showed up there in terms of total burning and uptake are flexible, and there could be a problem with that. But I do think that it's reasonably well balanced. I couldn't give you a number. When I said that I thought things were in balance, I meant pre-industrial, when the CO2 of the atmosphere was more or less constant. Okay?
So my follow-up question is that if we don't really know where about 15% of the total CO2 is going on an annual basis, does that actually mean we ought to be preparing for a worst case? Can you just explain the worst case scenario with atmospheric CO2 and rate of warming and perhaps sea level rise? I know there's a there's a boundary around these estimates.
I don't think that I can address that. That's a little bit beyond my background. I do think that we have really good information on the burning of fossil fuels and the inputs into the atmosphere. Certainly we have incredible measurements of the CO2 in the atmosphere, which are really robust. I would guess it's on the uptake side, so that there could be some issues. In particular, I think knowing what the biological uptake on terrestrial ecosystems is a very difficult measurement to make. And there's only 2 sites that I know of that make continuous uptake measurements in the ocean. So there's got to be a lot of flexibility there. So, but I don't think I can give you a worst case scenario.
Questions?
Hi, Don Gomez, Coastal Resources Council. And I appreciated your remarks on the submarines because I'm approaching 50 years with a local Navy lab in that area. So, but at any rate, my question is really on the modeling of the ocean and the effects, the vertical upwelling. And has that been accounted for? It seems to me that in the past that was one of the things that was neglected in the models. Could you enlighten me a little bit and how are we doing there and what's the effects of that going to be? Thank you.
Yeah, I think that the models are continuously improving. In many respects, the earliest models, and many of them still do, at the largest scales, use a single vertical mixing profile in order to mix the ocean. So the upwelling parts of them might be not well constrained in the global ones, but they're getting better. But there are higher resolution ones that are operational with groups like the Navy and stuff that I'd have to look into to see whether or not they're getting it better. But I do think that vertical mixing in the oceans is a critical aspect of the modeling that is has traditionally been well behind the atmospheric modeling and vertical mixing in the atmosphere, convection in the atmosphere, convection in the oceans, and upwelling is another side of convection, essentially. So, yeah.
We're going to take a webinar question. Stand by. The technology is so thrilling. I learned a new word in your talk, a gigaton. I'm going to use it with my 7-year-old. She's going to love it. A question from Alexander Clark. What does the science say about the relative proportion of climate change and sea level rise from anthropogenic activities? People, us.
I believe that the science would say that all of the recent sea level rise is anthropogenic, due to approximately 50% being the warming caused by fossil fuels in the atmosphere and increased greenhouse effect, and the other 50% being about the melting. That's what I'd say is the basic. Now, sea level can change due to changing larger scale systems, like sea level changes when there's an El Nino event. But those are oscillatory things, so you'll see sea level go down, then sea level come back up. But if you're talking about the long-term trends over the last several decades, I think that the science would say that it's nearly all caused by humans.
Thank you. Questions on the other side? I'm trying to be fair here. There we
go. My name's Joe Bingaman from Yukon Avery Point. My question was on the winter sea ice. Is it proportional, the recovery, or is it about as far down as the summer sea ice?
So,
ooh, sorry, we lost power for your PowerPoint, so you're just going to have to wing it. But you can do that.
So, I actually, in the interest of meeting the timing deadline, I skipped over the slide that had the histories of the seasonality of sea ice. So there was a figure, and I can show it to you separately offline. Since about 1950, most of the changes in summer sea ice have been in the summertime. But in recent 20 years or so, there seems to be some evidence for reduced aerial extent in the wintertime as well. So what happens is that, it gets really cold every winter because it's just completely dark. So it always freezes back somewhat. Only recently has it started to show up as less aerial extent in the winter than, say, in 1950. Now, that's not the same for the volume of the ice. As the melting is going on, volume seems to have gone more or less continuously down. And so you can think of this, remember how I pointed out that ice is generated in the Beaufort Gyre, and it circulates and it's ejected into the Atlantic eventually. Now, prior to the warming and the melting trend, in general, ice had about a 6-year lifetime in the oceans, in the Arctic, okay? It would form, and it would, on average, stay in the Arctic for about 6 years before it was ejected into the North Atlantic. Now, what that meant was that in any given year, you could find ice there that had just frozen that year, or you could find ice that was 2 years old, or ice that was 3 years old, 4, 5, 6. So the average age of the ice has actually decreased a lot because you're melting back so much of the old ice rather than and then producing more young ice. So the ice is thinner, and even though the aerial extent in the wintertime is still fairly extensive, it seems to be a little bit less than it was, but it's much thinner and much younger ice.
Thank you. Oh, so many hands. Woman in the back had her hand up first, so we'll go back there.
My name is Catherine Weaver. I'm a landscape architect and a board member of the Rhode Island Nursery and Landscape Association. My question is, what about the processes that you described have accelerated sea level rise on the northeastern seaboard so much more than other places in the world?
That's a hard question. I don't fully know the answer, but portions of the eastern seaboard are still adjusting to the fact that they were near to the ice sheets of the last ice age, maximum 21,000 years ago. And so the closer you are to those types of locations, the more you have to account for both the changes in the level of the sea and changes in the ground itself, the movement and the adjustment of the ground. And I couldn't give you specifically whether like Rhode Island's coastline is actually rising or falling in response to that adjustment. But we could figure that out, or we could look it up. But one of the things that you have to account for is the dynamics of the Earth's surface itself, as opposed to just the water, the full surface. So, yeah, that's as far as I can go on that without going out of my comfort zone. Sorry.
We'll go back to this side.
Hi, I'm Ron Tardif from University of Connecticut, Avery Point. You say that sea level rise happens at 3 millimeters per year, but what does that actually look like on land as far as how we notice the impacts of that? Because 3 millimeters seems pretty negligible.
That's a hard question. I mean, none of the coastlines are natural anymore. So I'm not really sure how, I mean, if it was a natural coastline and it had a relatively stable isostatic adjustment, then there would be small migrations of the beach towards the land. And, but I think that those are being fought in every step of the way by communities. So I'm not really sure how you see it. I mean, I think the sea level rise aspects of the climate problem showed up mostly as an added part on top of the storm surge that flooded the subway systems. I think that that's really, you know, that's the type of thing that if sea level was a foot lower than it was a foot lower than today because it hadn't risen so much, then maybe the subways wouldn't have flooded. Kind of a threshold issue there. So that's one way that, you know, that you have to think about this. I mean, a storm surge is a product of the intensity of the wind and the current sea level. And if sea level is going to be 3 feet higher in 100 years, and you still have, you know, 18-foot storm surges, then more subways are going to be flooded. So that's how it actually, I think, shows up mostly, in my view. Now, the relationship of coastlines to sea level rise is going to be a really complicated and interesting legal issue, I'm sure. You know, I'm sure you'll be talking a lot about it, but it's really hard to see and identify natural coastlines and say, oh, there's the effects of sea level rise on this coastline. You can see sea level rise reconstructions in some of the marshes and things like that that go back, you know, where the last 1,000 years of sea level are easily reconstructed in some coastlines. But to see what's happened in the last 50 years due to human input is not easy to see.
Hi, I'm Allison Reeser from the University of Hawaii. Dr. Curry, I thought that was an excellent presentation of what we know and how we know it. And I'm wondering, I'd like to shift the question to a question of science communications. And I'm wondering if, in your experience of making these presentations like this, have you ever had a confirmed or paid climate denier in the audience, whether it was a lay audience or a professional or scientific audience? And do you think that climate and ocean scientists have been silenced by this campaign that ClimateGate and the release of the emails from the University of Anglia has had on sort of the public perception of the scientific consensus?
In my most recent career, I was the head of the Ocean and Climate Change Institute at Woods Hole, and one of my jobs was to communicate the results of climate to a number of different public audiences. One of the public audiences were the trustees themselves of Woods Hole, who are often accomplished, very smart business people who've made lots of money, some of whom completely deny climate change. I mean, these are board members of one of the most respected scientific research institutions on the planet, and they're you know, just going in one ear and out the other. And there's one fellow in particular who I won't mention, who about every 6 months sent me the latest missive from the is it the Conservative Enterprise Institute or the Heritage Foundation or some, you know, who are writing these things, and you know, I'm getting that. After I stop giggling, I write back, you know, and I say, no, this is not true, this is not true, this is not true. And I always at the bottom say, you know, if you want to get scientific information, go to a scientific research institution, not a political think tank, okay? These are very different. So it's very clear that there's a battle of the truth here about this, you know, although there really is only one thing that's being governed by the natural, physical, and chemical laws of the planet, right? There is a battle for perceived truth, and it's been very difficult at times to convince some people. And you know, at some point I gave up on certain individuals and concentrated on those who were willing to listen. So.
And that's why you're here today.
No, I mean, I've always taken an approach that this is a country where a large fraction deny evolution and think that the Earth is less than 10,000 years old, okay? And I will never change those people in terms of the facts about the natural history of the planet. It's just not going to happen. So I tend to focus on trying to, you know, influence the people that I can. Yeah.
We are going to have a presentation tomorrow by Jeff Feinberg from the Yale Center on exactly on what people think about climate change, and it should be very interesting. We have time for one more question, and we're going to go back over to that side. Last chance, that side of the room. Here you go.
Hello, Diava Lambert from the Connecticut State Department of Energy and Environmental Protection. I really enjoyed the presentation that you gave, Dr. Curry. I actually thought I knew everything there was to know about climate change already, but I actually learned something today, and that's what you mentioned about what's occurring in the fjords in Greenland. And I was wondering if you could just expound on that a little bit regarding the science behind why just under the surface the water is a little warmer than the actual surface water.
Do we have power? Sorry, we don't. Okay. So seawater distributions are controlled by the density of the water. And water that is warm is less dense than water that is cold. That's the first foundation. Water that is salty is more dense than water that is fresh. So I'm in Bermuda now, right? The water there is warm and salty. Now, if I was in Greenland, the water there is cold and fresh. The relative densities of the water as they're set up in the modern circulation system is such that the salt content of the tropical waters in the Atlantic are the saltiest of the whole open oceans, Pacific, Indian. So those waters tend to be denser than the fresher marine waters that are coming from the Arctic, which are influenced by the melting of the Greenland ice sheet and also high precipitation rates of rain and snow at higher latitudes. So when these two waters meet, the northward flowing tropical waters heading towards Iceland and into the Norwegian Greenland Sea meet up with the southward flowing water coming out of the Arctic, which is ejecting this ice, and ice melts to become fresh water. The relative densities are such that the warmer water, which is saltier, is underneath the colder water. And it's physically constrained. It has to be that way, given the certain circumstances that we see. Now, it was like that probably 1,000 years ago as well. And that warm water was touching the glaciers and melting them because the whole system has always been dynamic. You grow ice at the summit of Greenland, it flows to the coast, and it melts away. What we think is happening in recent years, though, is that the warming of the waters that are flowing to the north might be accelerating the melting. But again, I reemphasize this, that discovery is only about 5 years old, that those waters are so warm. And so the monitoring systems are only just starting to get in place to monitor whether or not those marine waters are warming and whether or not they'll have significant impact on the ice sheet. But melting the ice sheet from below is one way to destabilize it more rapidly and to increase the rate at which it contributes water to the oceans.
Please join me in thanking Dr. Curry for a fabulous presentation. And you're here both days, yes?
I'll be here
so
tomorrow. Yeah.
Available to chat with you offline. Speaking of offline, we're going to be taking a half-hour coffee break, and we will come back at 10:15. Thank you. Thanks.